Okay, in part 4 of chapter 5, we're going to start talking about gravity. All right, back to Newton here. Newton had his universal law of gravitation that he used, the math he worked out there, he used to explain the motion of the planets around the sun, the motion of the moon around the earth, the motion of satellites, all of this. He explained it, used this to explain everything. And one of the things that comes out of that is the force exerted by the moon on the earth and the force exerted by the earth on the moon are one and the same. I weigh about 200 pounds. That means I exert a force on the planet Earth through gravity of about 200 pounds. Now, I notice this. The Earth doesn't care because the Earth is so much bigger, right? Or in terms of SI units, I weigh about 190 newtons. It means I exert 890 newtons of force on the Earth through gravity. Newton's formula for gravity is very straightforward. We have the universal gravitational constant G, which is this number down here, 6.673 times 10 to the minus 11th Newton meter squared per kilogram squared. Right? We have the universal gravitational constant. We have, as in the last example, my mass, m, the Earth's mass, right? And the distance between my center of mass and the Earth's center of mass. You're like, oh, what does this term mean, center of mass? Well, if you think about a ball, it's pretty straightforward. The center of mass of a sphere is at its middle. Center of mass of a sphere is at its middle. We're not going to get into the calculus of calculating the center of mass for other shapes. We're just going to often say, hey, the middle of an object that's uniform in some way is its center of mass. Right? And gravitationally, we can treat the object as a point particle at its center of mass. The calculus all works out. We can treat it as a point particle at its center of mass. So for this equation, we treat me as a point particle, we treat the Earth as a point particle. We're separated by the radius of the Earth, right? Because the middle of the Earth is where its center of mass is. All right, you might throw in an extra, 0.75 meters to get up to my center of mass, or maybe a meter to get up to my center of mass. But the distance separating us is basically the radius of the Earth. My mass, the Earth's mass. If we even did this with two pencils sitting on a desk, right? The center of one pencil, the distance from the center of one pencil to the center of the other is the radius we would use here, the distance between them, the mass of one pencil and the mass of the other. Now, when we start talking about pencils, why don't we notice this force all the time? Well, look at the universal gravitational constant, 10 to the minus 11, right? So if you're talking about a pencil that weighs, 0.01 kilograms, and another pencil that weighs 0.01 kilograms, and let's say they're a whole meter apart, right? 1 meter apart, then this force, that's 10 to the minus 2, 10 to the minus 2, that's 10 to the minus 4, 10 to the minus 15 newtons, right? 6.67 times 10 to the minus 15 newtons. We're not going to notice that, right? That's why we don't notice the gravitational attraction between everyday objects. That's why we don't really notice until we get up to objects the size of the Earth. All right, so two people. Different example. Two people with a mass of 50 kilograms each, 1 meter apart. So we can stick all of that in, and we get 1.67 times 10 to the minus 7th newtons, 10 to the minus 7th newtons, right? So the drag force due to the wind at 5 miles per hour, about 2.25 meters per second, is 3 newtons, right? I mean, the wind is exerting much more force on you than this gravitational force between two people standing a meter apart. All right, now back to center of mass. Since it is our center of mass that matters, if you look carefully at what goes on between the Earth and the Moon, the center of mass of the Earth and Moon as a group, while it's inside the Earth, it's not at the center of the Earth. So if you look at the path of the Earth as it goes around the Sun, it actually wiggles back and forth a little bit. Why? Because it's the center of mass of the Earth-Moon system that goes in a circle around the sun, or in actuality an ellipse around the sun, right? Goes in an ellipse around the sun. It's almost a circle, but it's an ellipse. And then the Earth wiggles back and forth, and the Moon wiggles back and forth a bit more. All right. This is one of the reasons we have tides, that the Moon attracts the water towards it, and the water bulges out on the opposite side as well, right? So we have a spring tide, Earth and Moon, the Moon and the Sun on the same side attracting water that direction. We have a spring tide where they're on opposite sides, right? And then we have a neap tide, which is not as strong. A neap tide is when the Moon is off in one direction and the Sun is perpendicular to that. The Moon is a dominant one here simply because it is so much closer. The Sun's way over here. So combined effect is this 24-hour cycle to tides. They're predictable, and there's the 24 hours and the 28 days that it takes the Moon to go around the Earth to interact in a way that makes charting tides an interesting long-term prospect. All right, that's it for this piece of gravitation. We'll come back to another segment on Kepler's laws.